All right. Hello. Welcome, and thank you for coming. My name is Howard, and I work for Autodesk Forma. And today I'm going to talk to you about how we've, on our journey from a small Norwegian startup to now being a big tech at Autodesk, use these techniques to combine reliability, so quality of our code, and speed by what I've dubbed with our pushing to main mentality. This is both to empower our teams and our engineers, but also the story of how, as an empowered engineer, you take accountability for this stuff. So I want to lead my presentation with two of our most controversial points. First of all, we maintain no staging environment for our application. We only have production. And secondly, if you join our team tomorrow, we'll let you push straight to master on your first day. So why do we do these things? First of all, we have an internal value of optimizing for time to value. So this is both in, we believe that we want to optimize the time it takes from a product person has an idea until our users are using functionality to reap the benefit of this idea, but also in the way that we design our processes and all throughout. We do believe in empowered teams and empowered individuals. We don't believe in making up rules that limit them. We like to give them sharp knives and then expect them to handle them properly. And we do believe that that will empower them to innovate. We really believe in learning quickly. So we encourage processes that lets us integrate code quickly so that we can learn from production and from customers as early as possible. And we do believe that we want to minimize everything, minimize the quantities that we ship, and minimize our processes. And ultimately, what we strive for as a company is that we believe that there's a better way to build cities, and we believe that these processes is the best way that we can let our users do this. So the techniques that I'll talk to you about today, I think that you can take each of them and apply some part of them. But I want to set the context to kind of give you an overview of where they work for us today, so that you don't have these techniques in the void. So first of all, our product is a 100% web cloud-based platform for architects that they can do early stage building design. So they start off in a Google Maps like interface to create their project. Next off, they can order local contextual data from local data sources to build a model to put their buildings in. We have some simple, easy to understand drawing tools that lets you sketch out building layouts on your site. We have an extensive suite for doing environmental analysis. Here you can see our wind surrogate model. And when the architect has figured out a few different options for their site, they can go on and compare these. Here you're looking at a sun analysis for two different proposals on the site. And then they can contrast and figure out which options to go for. And then at last, they have a board feature now where they can do the storytelling to tell the municipality or the stakeholders in the project why they arrived at this proposal. That's our product in the market right now. With Autodesk and with Forma, our vision is for the next 10 years to build out a industry cloud for the domains that we are in: architecture, engineering, construction, and operation. And it's both code that we build and ship at Autodesk, but it's also the broader ecosystem. So the last few months, I've been involved in building APIs and enabling third-party developers to extend our platform. So that's the product that these techniques work well for. Next, let's look at our infrastructure and organization so that you can grok the scale that we operate at right now. So we have a bunch of web apps running in the front end. So whole applications, which maybe one team owns the whole application. Within these applications, there are some parts that are shared. So we have about 100 web components that we share across these tens of web apps. In our backend, we're heavily AWS based. So we have around 750 Lambda functions, 250 S3 buckets, 200 DynamoDB tables. We have a few ECS clusters for the heavier compute. And amazingly, we still have only 2 GPUs running for all of our ray tracing-based analysis. On the organizational side, we're about 93 product people, so designers, product leads, and engineers, which are spread out over 13 teams. And again, these teams are gathered into what we call blocks, which are approximately bounded contexts for these teams, with 2 to 4 teams in each block. And looking at the code, we have about 480 separate code repositories on our GitHub. So from that, you can tell that everything is trying to be small and solving one piece of the puzzles. There's very few like monolithical big code repositories. We use 3 to 4 main languages, Python and TypeScript being the most prevalent. So let's dive in. And I have about 11 of these techniques that lets us stick to a brighter future. So to give you an overview, the ideas that I'm about to describe to you is how we keep things simple, how we reduce risk and time to integration, how we reduce the consequences of doing errors, how we deal with continuous integration, how we try to learn as early as possible, how we decouple systems, how we stay accountable when errors happen, and how we play on a design principle called recognition. So let's start with the first one. As I said in the beginning, we don't maintain any staging environment, development environment like that. We only have our production environment. So the idea for this and a few of the other techniques is to keep it simple. And throughout this presentation, for each technique, I will describe an anti. And I tried to choose the word carefully. I'm not saying that if you do something that I describe here, that you're doing something wrong. It might be the perfect thing to do in your context. But I'm just saying that we evaluated the trade-off and figured out that we want to take a decision that's kind of on the opposite side of the spectrum from the anti that I present. So the anti for no staging is kind of obvious. It's maintaining a staging environment, maybe even a development environment, and then trying to have identical replicas for all of these environments. So let's first consider why do you have a staging environment. So my argument is that you want to separate your data and compute from the production environment. And if we start with why you would want to separate the compute, so let's step a few years back and say that your production server is obviously running in your parents' closet. It's a single machine with the code running and the database running on this machine. And let's say that you want to do something like a performance test. now you have a problem, because if you want to run the performance test on this machine, it's going to hurt your end users because you're using the same machine. So what you did is to buy 2 machines. So then you have a production server and you have a staging server, and you have this separation between data and compute for this thing. Luckily for us, someone came and built serverless compute. So what this means for us is that this is essentially AWS's problem. I deploy a function to the production environment, and I don't care about the server. That's AWS's problem. If I want to scale up this function or that function, I don't care about that, because that's their job. So the first point here is that we don't really care about these compute servers anymore. So I can essentially run my compute workloads in production without hurting my users. The second thing here is that we stopped using individual servers, right? We've moved on to database clusters. So we don't actually care about this single database servers anymore either. And the next invention that we didn't invent, but we're taking a lot of use of, is we don't have databases in our stack. We have tables. And again, managing that on database layer is AWS's problem. And that leads us to, I think, the single thing that I've seen that we kind of put into this is that why should we have 2 tables, one for staging and one for production, when we can have 1 table, and then we can annotate each row with saying this is a staging row and this is a production row. And essentially, when you combine this technique with feature flagging, which I will talk about in a moment, we can have an infinite amount of these environments running in our production system if we want to. Now, there is something to say about the security of this system. What we've decided is that the team that owns the table has access to this. And if I want to do some testing and need some access to production data in a table that I don't own, I need to ask I don't have direct access to this. I need to ask our users for consent, and then we have some granting in our auth logic, which is audit logged, and then I can have access to test on this production data. So essentially, if I don't own project 1 in production, I don't actually have access to that. So that's how we deal with not having a staging environment. So the next thing I want to talk about is how we deploy to dev. And when I say dev, I both mean my local environment where I do my direct development, and also if I want to have replicate environments running in production or at AWS. So again, the basic idea here is to just conceive of the simplest thing that might work. And it turns out that, boy, does this work. So my anti for this is, let's say that you have all of these environments and you're nightly doing a batch clone of your production data, and you're cleaning it for sensitive data, and then you're constantly replicating this environment, maybe locally or maybe a separate staging environment somewhere. All of that work, we don't do any. So an abstract view of our architecture looks something like that. We have all of these web apps running. All of them is hitting a API gateway layer, and then that delegates to our APIs. And some of our APIs call into other APIs. Now, if I want to have a local dev environment, and let's say that there's a user that has reported a bug in production, and I want to test on their data, the only thing that I do is to take this single web app, and then I git clone that. It can be one of these 400 repos that I haven't worked with. I run yarn install and yarn start. And now, instead of going to app.autodeskforma.com, I go to local.autodesk Forma.com, and I'm hitting my own development environment. But the clever thing it does is to proxy everything in production. So right now, I can use the app as if I was in production. But for the app that I'm running locally on my machine, then the code running locally will be served to me. And with all of these web components that I talked about, I might have part of my page which is running locally and part is in production. And then the data that I operate on is served from our production environments. So that's how easy it is to spin up a development environment locally. Second, I can do this for our APIs as well. I can just spin this up, test it locally, going towards production endpoints. And then if I want to test some part of that backend functionality that I just changed through one of our web apps, I just spin up that web app locally, and I change the proxy configuration for this single backend service that I'm also running locally. And then I'm essentially testing this locally. It's a bit more cumbersome. And in fact, what we do more is to have backend feature flags to test this. And then the last thing that I can do is to take a copy of this local backend service that I'm developing, and using stages for, we're using serverless a lot to deploy our production environments. I can just change the stage to a development stage, and that will make a replica of this production backend system. And then with smart proxying again, I can sew these together so that now I'm actually testing this as if it's deployed in production, but it's on my own version of it. So if this seems to be a lot of work to test 2 frontends and 2 backends, yes, but that's because in this context where we have tens of these front-end applications or 700 of these Lambda functions, this is actually a very simple way to test all of that locally. The next technique is one of the most liberating ways that we work, and it's cleverly simple. And I'm hoping that most of you are familiar with this technique. So the idea here is for us to do continuous integration. And my anti for the way that we work is if you have a long-lived feature branch, maybe as long-lived that you're making a separate staging environment for this feature branch and using it. So what we do is to merge that code into master or main from day one. And the technique that we employ for our web apps mainly is to simply put a query parameter at the end of the URL. And then you read this in the code. And then you're flagging new code or old code based on this single query parameter. And the nice thing about this is that it's instantaneously available to your end customers. So if you're shipping something that you want feedback on fast, you can do it. And they don't have to jump through separate hoops, or you don't have to spin up an environment for them to test. They can just go ahead and test this. You can also do this on like contexts in your current data model. So like, is your user an internal user? Or you can use more advanced techniques as having a third-party service, shipping your flags so that you can write complex rules, or just have a place to configure, yes, no, I'm shipping this. So I talked about the early integration for end users testing. A second thing that's very nice here is that if I'm writing this code and you're coming in and refactoring the same code, if I'm well over here on a feature branch that you don't know about, you'll go ahead and refactor the whole of master, and we'll have to deal with that integrating those two code paths later, but when I'm merging this to our main branch straight away, when you come in and want to do your refactor, you'll pick up my change, and you might even refactor my code on the feature branch. A second point here is that when we actually go to production with this change, we're not doing a large merge, which might be risky. We're flipping one flag. And in the instance that we fucked up and want to flip back, we're flipping one flag back. We're not reverting a lot of code changes. And if you do this correctly, you're making it reducing the risk for you eventually breaking your production systems. So this brings me to our fourth technique, which is for me the perfect example of simple is not easy. It's all about doing small incremental changes. And the technique I can teach you, but the mentality and the way of working is very hard to get right, to get the full benefit of this. But essentially, you try to break everything that you do into small atomic changes, and then you ship them as you go, and then provide incremental user value to your end users. So the idea here is to reduce the risk, because each change is small, but also to reduce the time to integration so that your code is integrated into prod and you're learning from production workloads as fast as possible. There's an obvious anti to this, which is a huge, humongous PR that changes everything and has a lot of conversation on it and maybe takes a few weeks to test and build and review and finally merge. All risky business, if you ask me. So I'll show you two ways that changes can be done here. And then at the end, I'll compare and comment what I feel are the benefits of the way that we work. So the first one is the anti-example, where I do a large PR. So let's imagine that we have this main branch. And the first thing I want to do when I want to build a new feature is to fork out and make my own branch. But what happens when you want to make a feature sometimes is that you notice that the code structure wasn't really there. So you start refactoring the code to fit your change. And maybe this is a 10-minute change. It's a sweeping change, so it changes a lot of code, but it's fairly quick. And when you look at it, it's a very safe thing to do because it was kind of easy for you to automatically do it. And you're very confident about this being correct. And sometimes when you do this, you stumble on a few bugs. So maybe the next thing that I do is on top of my refactor, I fix the bug. And then I'm ready to build my feature. And it's nice because I've just refactored all of my code, so it fits very nicely to the architecture. And then after a few days, I'll make a PR towards master. But then I suddenly realize that you have your change coming into master as well. And you fixed the same bug that I fixed in a slightly different way without basing it off my refactor. And you've built your feature. And sometimes, maybe this is the high value critical fix and feature that means that you will have a prioritized merge. So someone goes and reviews your PR and you merge it in and you're now stuck with this, I have this big merge conflict, which means it will be harder to review. Maybe it takes longer time to resolve the fix. And some other trade-offs I'll get to afterwards. So let's contrast this with another way of doing and shipping this as more small incremental changes. So the first thing that I do is to do my refactor. And when I'm done, I'll just ship it to production. which means when you start doing your fix, there's two scenarios. Either you start after you saw that I made my refactor and you're able to pick up my refactor straight away and build it off of that, or the other scenario where you don't, but at that point, when you're going to merge it into master or push it to main, you'll see my refactor and be confronted with this change that you have to make. Next up, I will try to push my fix, but oh, you've done the fix, so I can drop my fix. And you've had to do it on top of my refactor, so I'm happy about that. You can do your feature, I can do my feature, and at our company, we're done now. There is no delayed merging, there's no review of this. We can go on to the next thing. So the two largest trade-offs that I see with this is first off the time to integrate. So if we consider the PR change, my refactor that maybe took me 10 minutes to write took maybe 1 to 2 weeks until it reached the main branch and reached our end users. And with a refactor, there's two things that happens there. Maybe the code quality was better, so maybe we had some bug fixes that went in that were fixed earlier when we got the refactor in earlier. And then the second thing is that everyone else is confronted with my refactor earlier on, so that they can now not have to do rework later when eventually my refactor lands. And the second thing I want to look at here is there's kind of two hiccups in both models. So in the small incremental changes model, it's when you pushed your fix in the scenario where you didn't pick up my refactor, and you now have to redo your fix on top of my refactor. But in this scenario, if you think about the amount of code and consequently the amount of test cases that we have to run over to ensure that this code is correct, you have just made your fix on top of master, so you know the code structure for master. What you need to read is my refactor, and then you need to apply the change that you just made on top of this refactored code. That's the amount of knowledge that you have to put in your head. With the PR scenario, the hiccup is when I have the merge conflict. And at this point, all of this code is in my head, because I've probably started to forget about how master looked like a week or two ago, because I'm in this happy place where I just refactored all of that. So that's where I'm at. I have to learn about the fix that you made in a slightly different way that I did. So I need to figure out that was it the same bug that we squashed? Maybe it has some trade-offs. I also need to learn about your feature, and I need to remember my feature. And then I have to test all of those test cases to ensure that we're not breaking production. So out of this, I have a few thoughts. So when you work in this more incremental changes method, each change is very small and can be reasoned about in isolation. Others are able to pick up your changes right away. They don't have to wait a week until they can base their work on what you've been doing. If you need to roll back something, let's say that that merge that I did to master failed in some way in production. My option is to revert that, right? That's a lot of code that goes back. With the smallest possible incremental changes, when you mess up something, it's likely that it was what you just did and that it's very small. Now, I talked about that this is actually a mindset change. You need to change the way that you develop the code from when you have the idea of what to change to break it into these continually incremental changes. If not, you're not reaping all of the benefits, and you'll actually have to fight this process. So this, I've watched a few engineers at our firm that are able to do this, and it's incredible to watch them. It's also one point that I might be missing here, that they are always done with their work. Maybe if you ask them, they're like 30 minutes or 20 minutes into what they just started, compared to the big PR. If you ask me about something 2 hours before I'm done with that big merge and testing all of those things, I've delivered nothing for the past 2 weeks. So I'm worried, like, I really want to do this one thing. So if you ask me about flexibility to prioritize something else, it's just 2 different scenarios. I'm not saying that code reviews are not valuable. I do a lot of code reviews, and I also ask for a lot of code reviews. But there are alternative ways to reap the same benefits as code reviews, without like making that a rule for your team that you have to go through code reviews. Our 5th technique, which is here mainly to set up the next one, because I've only seen this maybe used once or twice, but it's easier to explain, is blue-green deployment. And the base idea for this technique is that you want to reduce the consequence of doing an error. And the anti for this is taking down a central service in a very obvious way where you get a bunch of 500 errors in your logs and annoyed users. So this technique, I'll describe it with an example where we have a front-end application and an API. So what you do is that you stick a proxy layer in between your front-end application and your API. And then when you're deploying new code, you deploy both the old code and the new code at the same time. And this proxy is responsible for picking which of these to send new requests to. So it starts out with 0, and then it gradually increases the traffic that's going to the new API. And at the proxy layer, you're monitoring and observing the rate of, let's say, 500 errors to 200 successful status codes, and you have some sort of threshold. And if you cross above this threshold for too many errors, you simply scale back and you notify the engineers that, oh, there's something bad here. But in the instance where the metrics is looking good, you'll start to increase more and more traffic towards your new API. And then in the end, you'll have all of your traffic going to the new API, and you can tear down this infrastructure around it, and then you only have your new API. Now, this can be done automatically with plugins, so that the only thing that you know about this is if you've done something wrong, you'll be pinged by a metric saying, hey, your code is not deployed anymore, go fix it. So this brings me to the technique that we've employed a lot, which is to move this from the infrastructure layer and into the application layer. Now, this technique is inspired by a library by GitHub from quite a few years ago, which is called The Scientist. And the base idea is that you push your new code path with your old code path, and then you monitor application layer metrics instead of infrastructure. So the base idea here is to force us and allow us to learn from production workloads as early as we can. And my anti, it's a bit contrived, but I like to draw one slide at least. So let's imagine that you have a production system running your main branch deployed to production, and then you make this long-lived feature branch, which you also deploy to a staging environment. And if we compare these two with the amount of testing that is going on both of these branches, and ideally production data testing these branches. So for the main branch, from the start, you'll have a lot of traffic, like a pulse of your main production workloads. And then for this staging environment, you'll have some exploratory testing, the testing that you do when you develop this feature, and then right before you want to go to production, you're ramping this up and like doing an acceptance test or something like that. And then you flip the switch so that all the traffic goes from production over to your new branch, and then you're done. So the trick with the scientist pattern can be summarized as simple as this piece of code. So one try, that's to protect your users from you messing this up, which is very important. I've seen this tried out once without the try catch, and that was a bad idea. It's one if, which with a random variable that says, give us not all of the production workloads, but like 20% of it. And then you can see that I'm running my new code, but I'm not doing anything with the results of this. And then at the end, I'm running and awaiting my old code. Most of our backend is kind of asynchronous architecture. So when I do something like that, I'm not actually, like I don't care that I synchronously added a few lines to production code, because it's not going to give my end users a noticeable performance degradation. But what happens when you do this, and we do this from day one, is that you start learning about edge cases, and you start learning from production workloads, and you start to grok the performance of your system and how it scales. This is what you can do today. Where we took this was to say, okay, but we also want to look at the results from this data and compare them. So a few years ago, I was on the analysis team in SpaceMaker at the time, and we wanted to swap our infrastructure running ray tracing from Kubernetes to AWS and Lambda. And what we did was to employ this technique. I think this is approximately the code that I actually shipped. And in addition to running these on two different environments in production, we added a context variable going into the request, so that when it came to the time to store the analysis data back, it stored it with this context. And this meant that we were able to store the analysis results from the routine running on Lambda into one part of our database, and the production workloads in the other one. And when our users were using our application, they only noticed the production context. And we also employed a feature flag in our front end to let our developers play and use these different contexts. And you can notice that these are just strings. So I talked about infinite amount of environments. In this way, you can just spin up as many of these as you want. Luckily, we didn't need that many. So the additional steps that we went through here was to write a new program that would copy down the analysis results. And this is just basic lists of numbers, and compare them for to ensure that we had done the right thing when moving between these things. So when it came to the time when I flipped the feature flag to put all of the workload and kind of remove the old Kubernetes, I was very confident that we could do this without any downtime, and that we were handling all of the edge cases correctly. And I think we had one analysis failure, and that's was mainly because we didn't fit it in RAM, which is something that you need to configure for. All right. Next technique is how we do breaking changes. And as all of these techniques, like nothing is invented at Forma, but this is how we do it. So we combine feature flags and a known technique called expand and contract whenever we're doing breaking changes. And the core idea of this technique is to decouple systems in time. So my anti here is a launch announcement that next Monday, from 2 a.m. in the morning, we need to take down our system because we're doing like a large change to 6 of our services, which we've tested extensively in our staging environment, and we're shipping it to production. Not so lucky, 4 hours later, we noticed the world about an incident where we had to roll back this change because there was an unforeseen difference between our staging and our production environments. I lead this technique because I think it's brilliantly simple by a front-end and a back-end API. So the way that you totally decouple this is described here. And this is a simple HTTP endpoint, and sorry, I should have made up a few other words here, but I'm saying expand and contract. That's kind of making things bigger and making them smaller again. And then I'm saying contract, which is an agreement between two parties. So bear with me on that. So the contract here is the data that you pass from the front end to the back end. So when you're doing a breaking change in an expand and contract manner, what you do is to expand the API by adding the old version and the new version at the same time. Next up, the front end implements the version 2 of this API. And then in the last phase, you contract by removing the old version. Now, this is very useful when you're doing breaking changes to live APIs in this manner. But we'll see how this is very much more useful when there's a bit more complex system like this. So if we look at 2 front ends doing the same request to the same API, essentially with this technique, we've now decoupled these 2 front end teams in time from doing this change. So we don't care when they do them. We don't have to tell them by a date that they need to do it. And more complexly, if this contract is something that more APIs and backends serve, again, we've decoupled in time when this change needs to happen. Like, there is one coupling, and that's that a front end cannot add the version 2 until the backend has actually added that version 2, but that's the only, and that's not kind of a in sync coupling. Now you can notice that the first front end here is doing a small trick that will come in handy later on, is that it's actually consuming contract version 1 from the first API and contract version 2 from the second API. Now, I said to you that our system is a bit more complex than just 2 front ends. So essentially, we have plenty of these front ends and back ends. We call them producers and consumers in our system. So a producer would produce a piece of geometry, and a consumer, like a daylight analysis, would look at that geometry and analyze it. But there's a contract between them on how the data formats might look like. And the core idea for our vision for the 10 next years of our industry cloud, there's actually no upper limits to the number of producers and consumers in our system. And on top of that, we don't only have one contract, we might have plenty of contracts doing changes, having changes in flight at the same time. So let's consider how you would do this change to a lot of front ends and back ends is in a more traditional system. So you would start at the first phase of defining the contract that everyone is about to move to. And then you would ask all of your APIs to implement this contract. And then you would ask all of your front ends to implement this contract. And then you would have all of them coordinate to ship this to a staging environment, test it there, and then you would push to production. So in this, there's 3 sync points, which couples all of these teams and systems together. First of all, everyone has to agree that this is the contract that we're going to implement now. And everyone has to deploy to the staging environment before it makes any sense to do testing. And then every team has to test their system, and an acceptance test on the system needs to be performed in a sync way until you can go to the production phase. So let's compare this with the phases in expand and contract. So the first phase of expanding these producers to add the new contract. The second one is for all of the consumers or front ends to consume the new contract. And the last one is for the producers to deprecate the now old contract. So there is a sync point here as well. And that's at the point where you kind of ratify this contract. But remember my trick of when one producer and one consumer, or one front end and one backend API has adopted the new API, there's actually a point in time where you can do learning. And remember that we're running this straight in production. So we're getting user feedback on the feature that we are able to build on top of this contract at this point. So what we usually see people do is to, when this first producer produces this geometry, then a consumer comes in. And in most cases, it's actually this consumer that's pushing for this new contract. They want to have a new feature that they need a contract change for. So this pushes this sync phase where these two develop and figure out and iterate on this contract to earlier on in the process. And then I can push it out to the rest of the organization. So I also have a few thoughts and reflections on these different ways of working. So the first thing is, if we compare how long it takes from a product person has a great idea of a new feature until a user is actually consuming the benefits of this. In the traditional way, you need to wait until you've deployed to the production environment, which might be weeks or months after you had the idea. Essentially, if you're very quick about it, you can do the same within minutes with the expand and contract that we run. And again, the second one is about the size of things when things goes bad. So let's say that we learned something from this test in production, and now we need to make a change to this. So if you run a more synchronized and coupled process, there's a lot of people that care about this, and there's a lot of people putting a lot of their time into this. So when you come and say we've done a mistake, they're going to have a bad time. However, with our approach to this, maybe it's two teams, or maybe there's actually just one engineer on each of those teams that has learned this at this point. So they're much less invested in what you've done and open to changing based on new knowledge. And again, the second one, let's imagine the scenario that I talked about in the beginning, with this large change going into production and now being rolled back. Now, all of those teams that were done with this change and happy to move on to the next thing to build, they have to go back into that state and figure out what went wrong and eventually go through all of this ordeal again. Rolling back a change for two people that just started this, it's much less hassle. All right, our next technique is testing your code. I hope you think, duh. However, our base idea here is that one size doesn't fit any for testing. And my anti might be a bit controversial, but something like a statement of 95% code coverage is a rule that we apply to all of our teams. So I seldom write automated tests. But when I'm changing a part of the code that's on a critical workflow, I do. And my point here is that I think that there's two axes that you need to think about when you're doing testing. The first one is how much impact does the change that you're about to do have? And that's negative impact. Like, if I break this, will it be bad for our users? So if you're changing like a drop-down menu somewhere in the product, what's the consequence of that? If that's selecting some obscure setting somewhere, maybe the consequence of that is low. But if you're now making it impossible to create new projects in your product, that's a bad thing. So I always think about these two things when I make changes, and then I adapt my testing strategy to it. And then I think the kind of unlocking thing in our stack is that whenever you're adding things behind a feature flag, and if you're doing that correctly, then you might take things that was on the critical path and move it down to lower impact. And then you can also spend less effort testing this. And when I say less effort, I'm not saying that you should test it less and be less confident of it, just saying the time that you spend to build that confidence. Our ninth technique is dumb code. And I'm proud to say that there's a lot of dumb code at Forma. Again, the idea here is to do the simplest thing that's conceivably possible to make it work. And again, my anti is a notion of testable code where you've added a lot of abstractions which maybe are unnecessary to just make it testable. So I have 3 statements for dumb code. If I can copy-paste code from anywhere and stick it anywhere and it just works, then it's dumb code. If I can control-click on a function and I actually go to the implementation of that function, not some random place, then it's dumb code. If I can inspect the usage of some part of the code and then I find everything directly and explicit, then this is dumb code. So the nice thing about this copy-paste ability is that this code now has the lowest possible number of external dependencies. And the nice thing about the control click is that then this is probably built with the simplest possible architecture, no additional abstractions that I don't need. And the last one is that I don't have any unexplicit dependencies. So when I change this part of the code, I know what I'm breaking. So I know how to fix that. So I don't get stumped by unwanted consequences. Technique number 10. I hope that you know about this. I won't go into very much detail. I'm just keeping it in here because it's fairly important, and I don't think we're making any novel stuff here. The base idea for this is to ensure that your team is accountable for everything that they do. And the anti for incident management is to don't care about stuff going wrong. So we do 2 processes for incident management. It's when the incident has happened, then we have a process for dealing with that incident as quick as possible with Zoom rooms and commanders and assessing impact and severity to ensure that the impact to our end customer is as low as it possibly can be. And then we have an incident review process for our teams. So after an incident, you do this, both to build a confidence that you're failing together in a blameless way, but also to learn from your mistakes. Our last technique is log contexts. And the base idea for this technique is to employ the recognition design pattern, in contrast to recall, where recognition is the ability to recognize something that you've seen before, while recall is the ability to, out of thin air, remember what happened. And the anti for log context is this amazing thing that tells us everything about what went wrong. So I have 2 examples of how we employ log context at Forma. The first one is whenever there's a data order that fails in our system, we have a Slack bot that will at us and tell us. And this, I mean, it's maybe more than 2 years since I designed this system. And when I looked back at this message the last week, I actually remembered the architecture of this system because it told me all about it. And it even kind of gives me some lines of code that I probably wrote at some point to remind me which line this failed on. It reminds me how I can reproduce the thing locally. It gives me a shortcut to retry this error. It reminds me where the logs are. And when I look at the logs, it's reminding me of how this system was composed and what parts it's built of. So this brings us to my conclusion. So again, we employ these techniques to take accountability when we are given the sharp tools so that we can keep empowering our teams, so that we can integrate early, optimize for this time to value, and try to minimize all of the things that we do. I told you about all of these ideas, from reducing risk to continuous integration, for decoupling, and maybe also learning early. However, this doesn't exist in a vacuum, and we've made these decisions because it works for us. I'm amazed how much of this is true now and was true 4 years ago. But there are trade-offs to this. So first of all of your engineers must act accountable, and you need to trust them to do so. If not, this breaks down. You need to embrace the chaos, because you're not this is about not putting in, like, there weren't any rules here. I'm not saying, and not all of our teams do these things, but they can do it. So you need to embrace the chaos of autonomous and embraced or empowered team and dynamic. This is brilliant for having high iteration velocity. If I have an idea, it can be seconds till a user is testing my idea, if I want to. And it allows you to always minimize the time it takes to correct the issues, because there's no artificial boundary before you fixing a bug. You don't have to ask for permission. Security becomes something that everyone is responsible for. So we're not putting that to a centralized unit that decides a lot of things for the rest of the company to protect them. We're pushing that back into the team, and that's a real trade-off that someone thinks is very hard. You need to embrace incidents because they will happen, but it's how you deal with them that's the most important thing. And then in our context, we are still iterating on our product. We're trying to get it to grow. That's what we're mainly focused on. And if you're not in that state, maybe other trade-offs makes more sense. And this is my last slide. I'm Howard. If you want to talk about these things, I'm here for the day, or you can talk to me at LinkedIn. Thank you.